by S Sathyaprakash. This is probably on a slightly different topic, but it's very related to numerical-relativity, and he's going to place this numerical-relativity in a bigger context of gravitational physics and astronomy. Okay.
Thank you very much, Ajit. Thanks very much to Ajit and the organizers of the school and workshop. I left this campus 1988. I did not imagine that I won't return for 25 years. Okay, so it's even though I have come to Bangalore quite frequently, almost every year since then, it's only this year that I have come back to my campus where I did my PhD and the first year of postdoc. When I was here, I didn't do any gravitational waves, although I studied a little bit of it. Bala Iyer, sitting there, taught us general relativity right in this building. So thanks to him and teachers like him, we are today able to take the field forward, and I'm very happy to be able to tell you something about gravitational waves. My lecture is actually two parts. One is today, as a part of the school, it's more elementary, more basic, but on Tuesday, I think next week, it will be probably even more basic, even more fundamental. So I have tried to avoid any overlaps between these two talks, but it is extremely hard to cover the title of this topic, which is Overview of Current Research in Gravitational Waves. It's a very vast field. You probably need a school similar to the one that you have had on gravitational source studies using numerical relativity simulations. So gravitational astronomy is truly great. But why study gravitational waves? What's the big deal? Universe on very large scales is actually dictated by gravity. In fact, if anything, 20th century has taught us that there are three things that come out from Einstein general theory of relativity. One is that the universe was born out of nothing in a Big Bang everywhere, although that picture is probably wrong because you need to take into account quantum theory gravity to really understand what happens close to the phase of the universe when the universe was very hot and dense. But nevertheless, that's one of the predictions. The second is that black holes are the ultimate fate of massive stars and gravitational collapse. You really can't prevent black holes from happening. That's one of the predictions. And finally, that in addition to these solutions like black holes, you also have wave-like, that is non-stationary solutions called gravitational waves, and they are inevitable consequence of any theory of gravity that is consistent with special theory of relativity, as I will tell you in a minute. So these are the three predictions that were made by Einstein, and today we have evidence for all, but we haven't really observed directly any of them. We really haven't observed the Big Bang directly. There is indirect evidence in the form of cosmic microwave background. People tell you about black holes, black holes, black holes, and they show you movies, but they really haven't seen the signature of black holes. Gravitational waves, of course we have seen, and even the Nobel Committee has recognized that gravitational waves exist by awarding Hulse and Taylor Nobel Prize, but they are not observed directly. We have only seen consequence. If one of my collaborators, Thibaut Damour, were here, he would immediately rip me apart saying that what is observation? What do you mean by indirect evidence? Because after all, we have seen the effect of gravitational waves, and there is no way to really explain the effect of gravitational waves on the Hulse-Taylor binary pulsar. So we have really seen gravitational waves, is what you would say, but we can't really measure properties of gravitational waves by using Hulse-Taylor binary pulsar observations. They are fundamentally radio observations, and if you want to measure the polarization properties of gravitational waves, if you want to form the waveform in phase, you really don't do that. It's only an indirect observation. In that sense, I mean, it's only an indirect evidence for all of them. It's so nice to see this fan is causing ripples already on the screen, right? If you imagine that's the flat space-time as a wave passes, that's exactly what happens. Okay? The key to observing the first two is actually in the last one, namely both the very early universe. Hopefully one day we will observe direct evidence for the very early universe, and also direct evidence for black holes, ringing black holes, colliding black holes that you have learnt about in this past week by using the window of gravitational waves. So this lecture will really discuss what gravitational waves are very briefly, and then take you through to explaining how we can explore the universe by using gravitational waves. So on the larger scales, as I started off, gravity shapes the world, right? Matter is electrically neutral. The weak and strong forces really don't play any great role on large scales. And because matter is also electrically neutral, it really doesn't play any role. And gravity is the one that rules the world. It shapes the world. It forms the large scale structure. And stars and galaxies really feel gravitational pull of each other and nothing else. And so far, however, gravity has played a passive role in exploring the universe, in the sense that we don't really see this wave part solution of Einstein's equations. We see the stationary part or the static part of the solution, but we don't see this wave-like solution. But that's about to change with the construction of gravitational wave detectors. And over the next decade, we hope not just one method of detecting, but more than one method of detecting will succeed and explore the universe using gravitational waves. So the gravitational window then is what I'm going to talk about in this lecture, but probably also quite a lot in the next lecture as to what we might learn about the universe. So let's go back to the very beginning and look at Newton's laws of motion. Newton's laws of motion, once they are given, you have to tell what the force on the right hand side is, and one example of that force might be gravity, and gravity is described by this Poisson equation. The Poisson equation contains only derivatives in time. This is the 3 time derivatives, and gravity is described by a single scalar field, and the value of the scalar field now and here is given by matter distribution at a distant place now and everywhere. So the matter distribution is telling you what the gravitational field is, and the propagation of information, matter distribution, is instantaneous. The reason is there is no d square by dt square term here. There's absolutely no retardation. If the matter field changes now, that will immediately affect what the scalar field does, this single gravitational potential does. In general relativity, there are 2 essential differences. One, you replace this scalar field by a second rank symmetric tensor, so 10 quantities to begin with. Only 2 of them have really any dynamical meaning. So instead of 1, you go to 2. So that's one thing that happens. But in order to describe the theory in a covariant manner, you need 10 quantities. You can't do with 2. That's the reason why there are 10 here. But if you are in a gravitational field that is very weak, that is, there exists a coordinate system in which you can express the metric first of all in this manner, very small deviation from the flat space Minkowskian metric. So there is a very small addition, in the sense in some coordinate system you can express the metric tensor as a sum of the Minkowski tensor plus a small quantity. So that would be called the metric perturbation. And furthermore, if you choose a gauge, or if you choose a coordinate system in which these metric perturbations are divergence free, it's not those quantities themselves, but a new quantity called trace reverse tensor which should satisfy that. So if you use conditions of this kind, then Einstein's equations actually reduce to wave equations. So starting from Einstein's equations, instead of these single equation and a Poisson equation, you end up with a wave equation for 10 quantities h bar alpha beta. So the coefficient of this term, the inverse coefficient, gives you the square of the speed at which that wave travels. Here the coefficient is 1 because I have written it in unit c equal to g equal to 1. Therefore, the speed of propagation of gravitational waves is equal to the speed of light itself, and this right hand side here is the matter energy momentum tensor, and that is the source of the field. So if you are in vacuum, I mean, you can put right hand side equal to 0, you get wave like solutions, and they are pretty simple. So you can obtain plane wave solutions by equating h bar alpha beta equal to some second rank quantity a alpha beta e to the 2 pi I k mu x mu. The only condition that must be satisfied is that k is a null vector, and that's the reason why gravitational waves travel along the light cone and they have the speed of light. That's what I uttered just a minute ago. But if we go back to the previous slide and ask what these gauge conditions mean, h bar alpha beta comma beta equal to 0, they would imply that a alpha beta k beta equal to 0. It turns out that in addition to those gauge conditions, there are some residual gauge conditions that one can impose, and using all the gauge degrees of freedom that you have, what you conclude is that first of all you can make any quantity that has the time component equal to 0, and you can make all the components of A, which are the amplitudes of these wave like solutions, orthogonal to the direction of propagation. So Aij kj equal to 0 means it's a transverse wave, and moreover using these residual gauge conditions, you can make the trace of that as well equal to 0, because you actually don't exhaust all the conditions. There are only 3 conditions here and 1 there. Sorry, there are totally about 7 conditions that you exhaust by these, and you have 1 more which you can use to make the quantity traceless, and what you finally get is a solution in which the direction of propagation is the z direction in my chosen system of coordinates. Kx and ky are equal to 0, kz is k, and what you have is only 2 components of this amplitude equal to non-zero. That is, most of them are 0. Axy is nothing but ayx, it's symmetric, and ayy is minus axx, and everything else is 0. So the quantity that comes out of here, h bar xx, which goes like axx, right, is called h plus polarization, and the quantity hxy that comes out of it is called h cross, and the reasons for that will become clear in a minute. So got 2 solutions, and how do they affect the motion of test particles? We all have heard about the so-called equivalence principle. You can always put a particle in a freely falling reference frame, and you wouldn't notice the difference whether you are in a non-inertial reference frame far outside of any gravitational fields, or you are in a gravitational field but freely falling. You can't distinguish between those two. That's what the equivalence principle does. And that principle can be applied to conclude, in fact, mathematically, that the acceleration felt by any particle in a gravitational wave field is actually 0. There is no acceleration felt. You can completely make it vanish by choosing a reference frame in which it is freely falling. So by observing a single particle, unlike electromagnetic radiation where there are neutral particles, and here there are no neutral particles in gravity, and therefore you can't really observe acceleration on a single particle as a gravitational wave passes by. So a particle at rest remains at rest, and transverse traceless gauge, as it is called, because our quantities here are both transverse and traceless, that's why it is called a transverse traceless gauge, is a coordinate system that's co-moving with freely falling particles. But nevertheless, this doesn't mean that you can't detect gravitational waves at all. Often a confusion in popular literature, even with the second explanation that I will mention. So what you can do is to watch 2 nearby particles, and in a freely falling lift, if you watch 2 nearby freely falling particles, then as time goes on, both of them are approaching the center of the field, and therefore they are seen to approach each other. Okay, but if you make this whole thing change the curvature here being positive to negative, what can happen is that the distance can actually increase instead of decreasing. So if you, the key then is to take not one particle but two particles as in this freely falling frame and measure the proper distance as a function of time, and you can do that by what is called the geodesic deviation equation. The geodesic deviation equation is an equation in the separation vector xi, and the second derivative, which is like the acceleration, actually depends on the curvature tensor. So if the curvature tensor is 0, then there is no acceleration. That's the statement of the fact that two parallel lines will remain parallel forever. Whereas if you put any non-zero curvature, then that's going to affect the distance between two test masses. If they are initially parallel, they don't necessarily remain in parallel. This is true even in static gravity. If you take two particles on the surface of a sphere at equator and send them towards north, they're both going north initially, so which means parallel, but as time goes on they seem to converge, and that's what might happen here. They may also diverge in the field of gravitational waves because this components here can be either negative or positive. Okay, they can either converge or diverge, and if this is sinusoidal, it turns out that this curvature tensor for the solution that we have obtained actually is oscillatory. It's just the second derivative of the metric perturbation. So if this is sinusoidal, that's again sinusoidal. Two derivatives with respect to time will give you again a sinusoidal field. Therefore, the acceleration that is felt here is sinusoidal. So the distance between the two particles keeps changing. Many people, when I give popular lectures, ask me questions about, hey, if a gravitational wave is passing, it will change both the ruler and the ruled, the distance between the particles and also the scale itself. That's a naive concept. So what we are actually doing is, what I would like you to imagine doing is to perform an experiment in the laboratory to measure gravity itself. Forget about gravitational waves. Let's see whether we can measure gravity. What do? We can go here, and are you telling me that the scale actually shrinks and therefore I can't measure the distance between these two particles? That would be rubbish. The experiment has been done over and over again, and we can actually do in more than one way. We can actually measure the ticks of a clock sitting far away from the gravitational field, and the ticks of the clock, do they run slower compared to a clock close by or faster? What do you think? If I stay close to a black hole, do I age quickly compared to my cousin who is far away? I actually age slowly, right? So that's called the gravitational redshift. That has been measured. So we know how to measure gravity. If you know how to measure gravity, measuring gravitational waves is no big deal. You can use exactly the same principle, except that the ticks of the clock of the same clock compared to some standard reference, and you might say the reference might change. What I do is, I'll come to that, how to detect gravitational waves in a minute. We send a ray, right ray, to go somewhere and come back and keep measuring the ticks with respect to the return time of that light ray. In this way, we can actually measure a passing gravitational wave. Of course, if you sit in one place and simply look at the clock, you can't tell. You age in the same way as the clock itself. But if you are monitoring the return times of a laser light that is sent around in a gravitational field or a gravitational wave field, you can measure the presence of a gravitational wave. So if somebody challenges you, how can you measure gravitational waves? Don't be intimidated. The answer is pretty simple. It's really measuring gravity. It's no big deal, really. Anyway, so Einstein's equations actually can be used in order to not only infer that gravitational waves can be measured, but also associate energy and momentum with gravitational waves. Incidentally, this question really goes back to Einstein himself as to whether gravitational waves existed. There was a big controversy about the very existence of gravitational waves, which was finally resolved in a Chapel Hill conference in 1957, but the authoritative paper was written in 1959 by Bondi and collaborators. That finally laid to rest. So we are a pretty old field now by any standards, and it's a shame we haven't detected gravitational waves yet. But so how do gravitational waves really interact with matter? And I make the same point that the effect of gravity is no different from, effect of gravitational waves is no different from gravity itself. And this goes on to illustrate that. The fundamental effect of gravity is to cause tidal deformation of objects, and that is illustrated here. So you have Earth there, and different particles on the surface of the Earth feel different forces because Earth is an extended body. But if you go to a reference frame in which the acceleration at the center of Earth is 0, then you will see the tidal deformation of the Earth, because the acceleration towards the center of the Earth will simply make the whole Earth freely fall in the field of the Moon. But then if you look at the relative accelerations, it is a tidal field because these two are towards the center of the Earth, those two are away from the Earth, and typically tidal forces actually scale with size. The bigger the Earth, greater will be the tides. We are lucky we live on Earth, which is only 7,000 kilometers or whatever in diameter. We have small tides. If you are, on a Earth that is 10 times bigger, the tides will be 10 times bigger. The effect of gravitational waves is identical. A passing gravitational wave, so let's take a ring which is free to deform. There are no electromagnetic forces acting or nothing is holding, it's just a ring. And let's suppose a gravitational wave passes, that ring gets deformed in this manner. The change in length delta L compared to the original size L basically gives you the amplitude of gravitational waves, but for a factor of 2. So delta L by L is really h upon 2. So the measurement of that strain is what we are after. And how can we do it? You can do it many different ways, and I'll illustrate just one method by using laser interferometry. So consider two mirrors at on this ring, and you have a laser that is shot out from this source, gets into two different directions. It gets reflected back, comes back here near the beam splitter, and exits the interferometer towards the laser source. It can be taken out, but that's not a problem. Normally, there's no light going in this other direction. When you deform this ring, then what happens is the path length in the two different directions are different. As a result, you can have some of the light emitting in this direction, emitted in towards the photodetector. So this might be the configuration after 1/4 of the period of the gravitational wave. After a full half the wave, you recover the original configuration, and after 3/4, the ring gets deformed in the opposite way, just like the tides on the Earth. So you get some more light, but with opposite phase. So by monitoring light that is exiting the interferometer, you can actually detect gravitational waves, and that's what I was describing earlier. In fact, if you have a very good laser source, you don't, or timing, a clock near here, you don't even need 2 arms. Just 1 arm is enough. You can send out that light and monitor its return trip times compared to the clock time. Okay, you have this mirror far away in space, kilometers, hundreds of kilometers, thousands of kilometers, millions or even billions of kilometers, and all these exist. All these type of different detection methods exist. Okay, hundreds of meters, kilometers, thousands of kilometers, or even millions and even billions of kilometer detectors do exist, and one of them will hopefully become operational and detect gravitational waves. I won't tell about all of them, but maybe mention a few little later. I think the biggest problem we face is that for typical astronomical sources, the change in length is 1 part in 10 to the 22. I'm really being silent now because that's a very, very small number. And that's the difficulty. That's the basic challenge. If you put long time ago, is that's no big deal. I'm after the phase. I'm after the difference in the arm length, not the absolute length, guys. So we can do that. So they went ahead and they made proposals and started building gravitational wave detectors, and I will tell you about them on Tuesday. What kind of gravitational wave detectors are coming up online and what can we expect to observe. I want to come back to theory a little bit and tell you how bright these sources are. They're not by any means, puny little guys sending you small amount of signals. If you go back to the Isaacson formula, you can actually work out the energy moment tensor in gravitational waves and ask what is the energy flux. And that is given by this formula, very simple. It's k square by 32 pi. K is that little wave number that we introduced. It's simply 2 pi times the frequency. A plus square plus a cos square. You take your favorite source, compute it. And that's what I did. I took my favorite source, and for that I computed the flux of gravitational waves by putting back C and G and all the stuff. Then I discovered that if I put this amplitude irrespective of where the source is, if I put that amplitude h of 10 to the minus 22, remember that's what I used in the previous slide, and I assume that the waves are coming off at 1 kilohertz, then I get 3 milliwatt per meter square. Even I put the source at something like Virgo supercluster, I might be able to generate a flux that is twice that of full moon for such a small amplitude. That only shows that gravitational waves interact weakly with matter, and thank goodness for that. Because without that, if gravitational waves interacted very, very strongly, the tidal forces that they generated would have really ripped us apart. Well, we wouldn't have probably come into existence in that case. But imagine that gravitational waves were generated only once in a while, and they would just simply come and rip us apart. So it's really that's what really helps us, this weak coupling. In spite of that very small amplitude, this large flux only tells you that the tidal deformation is small, even though the flux is very, very large. So this is the typical formula that you might remember whenever somebody asks you to calculate a typical energy in gravitational waves. All it depends on are really 3 quantities. One is how much of energy is in gravitational waves. It goes like square root of that. It goes like, it's not just the amplitude is not just the total energy, although what is called signal to noise ratio, the way, how well we can observe it really depends only on the total energy, nothing else. But if you want to compute the amplitude, then that depends on the total energy, square root of that, multiplied by how quickly it is emitted. So if you emit the radiation in a small duration, you will have large amplitudes. If you emit it in 1 millisecond, you have 10 to the minus 21. If you took 1 second to do that, then that would be a factor 30 smaller, and so on and so forth. But of course, the waves scale like 1 by r. So at 20 megaparsec, you might produce 10 to the minus 21. But if you put it at 200 megaparsec, it goes to 10 to the minus 22. So that is how it scales. It also scales like inverse frequency. So, if you go to higher, if you want the same energy but in higher frequencies, the amplitude will reduce accordingly. So that's the typical scaling, and for most of the calculations, that's all that you need. Not all the Einstein, complicated Einstein's equations. You can go back and do all the numerical simulations you want, but this is the basic formula that tells you how much of energy might come out. The difficulty is this number. How can you tell me that it's only 10 to the minus 2 of a solar mass and not 10 to the minus 5 or 10 to the minus 8 or 10 to the minus 10? And that's what these guys do. What these guys do is to solve and tell you what that number is, and that's where the secret is. But if somehow you can make a hand-waving argument, which people have done in the past, that's all you need. Okay? That formula is really a golden formula. So understanding gravitational wave sources, then most of the rest of this talk is really hand-waving. As I said, you need probably more than a week to do that. And I'll start with modeling compact binaries. Nothing that I'm going to tell you is going to be new, but it is only a summary talk, and I hope it's of interest. Post-Newtonian approximation is something that's been around for a pretty long time. It was used the very first time by Einstein himself to explain the precision of perihelion of Mercury, and has been tremendous success. But it's only valid when the velocities in the system are very, very small. I apologize for the poor quality of the slides there. Or when the compactness is small too. That is m by r, gm by rc square. I left out r, which is the typical size of the system, that makes it dimensionless. Otherwise, it has dimensions, and you can't use dimension for parameters for expansions. So this is valid really in the limit v tending to 0, but it's correct to all orders in the deformation parameter called nu. We are mostly talking about binary systems. So this nu here is the product of the two masses divided by the square of the total mass. So it's correct to all orders at a given velocity, but it's only valid in the limit of small velocities. Black hole perturbation theory, on the other hand, is used to describe small perturbations around black holes, like small particles falling into big black holes. And here this is almost like a test particle orbit in a curved black hole. This is the opposite of the post-Newtonian expansion, where it is correct to all orders in V, that is fully relativistic, but it's only valid in the limit that the test mass goes to 0. That is, this quantity here goes to 0. Effective one-body formalism is an improvement over post-Newtonian approximation. We haven't, I think, talked much about effective one-body approximation in this school, so I won't really tell a lot about it, except that it uses very clever summation techniques that have been successful in particle physics in computing electron G factors and so on. So it's really something that has been brought into general relativity very recently, but has been pretty successful, especially in the test mass case. It's remarkable how this so-called effective one-body approximation works so very well compared to exact solutions. Numerical relativity is what you have heard all about. It's an exact solution to Einstein's equations, but it is only as exact as your numerical method is. The more accurate you can make it, the more computing power you can throw at it, with a lot of intelligent computing power, not just CPUs, then it becomes better and better. The phenomenological models, I think Harold in his talk was referring to some of the phenom models. These are based on numerical relativity. They fit numerical relativity simulations, the waveforms actually, to the data, to some model. And Ajit and other people here have pioneered these methods, because without those phenomenological or analytical models, it's very hard to use numerical relativity simulations in gravitational wave data. So any of these fields are good fields for you to start with. So I think we will, in the afternoon there is a discussion session where I saw a question about, give us some advice, which ones. All these, except perhaps here, it's very, very challenging, because people have now gone on to compute corrections to the dominant order to such a high order. To make any more progress will require about 5 years. So if you are interested in computing the next correction, reserve 5 years of very, very hard work, and forget about eat and sleep and so on. So that's a very hard one. Black hole perturbation theory likewise has made a lot of progress, but I believe there is still quite a lot of scope there. Effective one-body formalism is a very active field to get in. Numerical relativity simulations obviously is a massive parameter space out there to explore, both in vacuum, which means binary black holes, but also with matter, which means neutron star black hole and neutron stars. In addition to these things, there are hybrid models which actually make use of the phenom or post-Newtonian and numerical relativity, and many different things exist there. It's a mixture of all these different things. And finally, field theoretic approach, which is the new kid on the block, and it's a very powerful approach. And these guys claim that they can keep going beyond the orders up to which post-Newtonian approximation has been computed. Just to give you a hint as to what's been done with post-Newtonian approximations, one has computed the energy, I believe now, to V by c to the power of 8, which is called 4pn, although the results might not be out yet. It may not be there in the literature. And this is the energy, Pn energy, and Pn flux has been computed to V by c to the power of 7 beyond post-Newtonian are called 3.5 pn. I think I spent too much of time on that slide, or what? What happened? This is a pain if you put this in one by one. I don't know in Mac how to get to the next page without going through all the bullets. The main challenge of solving Einstein's equations for binary black holes is depicted in this picture here. The signal from a binary black hole is really characterized by a lot of structure, which is what makes it very, very interesting. There is a slow adiabatic inspiral phase where post-Newtonian approximation has been very, very successful. But as I was mentioning earlier, most of the energy comes really from this final merger phase. That's because the luminosity in gravitational waves goes like h dot square, okay, whereas h goes like v by c whole square. Luminosity in gravitational waves goes like v by c to the power of 10, and that's because each of these dots will bring out a factor of omega, and there will be a omega square, and that will bring in, and omega square goes like v cube, and that will bring you a factor of v to the 8. Right? So you can do a simple calculation to show when you go from h dot square to luminosity, you get v to the 10, and a lot of energy is emitted here. So it's very important to get that phase quite accurately. Okay, that's the merger phase, which is handled by numerical-relativity. Most of this is actually handled by post-Newtonian, although I do have one comment to make with regard to Harold, you showing, what are the next challenges. I will mention in a minute a challenge that we may have to do in the inspiral phase. And finally, the ring down phase is handled by numerical-relativity. But this can be shown in one other way. The signal shape, of course, contains a lot of information, and we can extract it from gravitational wave observations. We can talk about this parameter space in a different way due to Blanchet and his collaborators. What is plotted here is the inverse of the compactness of the system itself, not the compactness of the body, compactness of the binary, namely R12 by m. M by R12 is the compactness. R12 is the distance between the two bodies. That's the inverse of the compactness. That means objects are more and more compact as you go up in this direction. It goes to infinity, the compactness goes to 0. Whereas what is plotted here is the mass ratio, log of m2 by m1. So these objects are, become more and more particle-like as you go along that direction. More and more particle-like, more and more relativistic as you go in this direction. Okay? What post-Newtonian theory has been able to do traditionally is to handle the situation where it is mildly relativistic, like Mercury. So that's why it is up there, and it really becomes valid, very valid as you go up in that direction. So that's post-Newtonian theory, and that's how the field started. But post-Newtonian theory plus perturbation theory, which became popular in the 40s and 50s, started tackling this part of the parameter space where you made the system not only it started tackling more and more relativistic region, not only relativistic but also assuming that there is the mass ratio is large, that is point particles. So it's really the field progressed in this direction. So post-Newtonian theory, perturbation theory was developed later. Okay, so it was fully relativistic, but only for point particles. But then this region where it is both relativistic as well as comparable masses is dealt with the mixture of post-Newtonian theory and perturbation theory. In order to solve the problem in this interesting regime, you are left with nothing else but numerical-relativity simulations, but then you can translate that into something like effective one-body formulation, and it can hopefully span the entire parameter space is what the goal is. but it's not just EOP, even phenom models should be able to do that. Okay, so a few words about post-Newtonian theory itself. It's been remarkably successful, and so successful that Clifford will at one point, I think I have a statement from him somewhere, unreasonable accuracy of post-Newtonian approximation is what Cliff Will used as a title for one of his talks in the early part of the success of numerical relativity simulations. But it probably is not actually very accurate for some of the simulations. I will come to that in a moment. So for most binaries, this waveform, for most binaries I mean most binaries that LIGO might see, this may be a pretty good approximation. It's quite remarkable that it actually agrees with so much with numerical simulations where it does agree, and that's why Cliff will use that thing. However, there are systems for which post-Newtonian approximation is not quite good enough. Even in that so-called adiabatic regime, mixed binaries consisting of neutron stars and black holes. And this is where I want to draw Harold's attention, namely, even though post-Newtonian seems to be very good in most cases, when you include spin and when you have long inspirals, post-Newtonian is really very crappy. It really doesn't help us.
If I convey the sense that I think post-Newtonian is good, I apologize. It wasn't my intention.
I can't really, in the sense that you guys need to do these simulations. We need simulations, at least a few, in which you have hundreds of cycles. Because, why am I saying this? People have compared different post-Newtonian approximations just in the inspiral regime, and they all seem to agree very well when black hole masses are large or they are equal and no spins, and that's all fine. But it's not great news, right? It's not hunky and dory. Yeah.
Is it a fundamental limitation of post-Newtonian theory, or reflecting the fact that the spin terms in the post-Newtonian theory are not calculated the way you have already?
Now they are available up to 2.5 pn. Maybe it's not enough.
Right.
Maybe we need to go.
Spinning them up to 2.5 pn were not good enough for.
That's correct. That's correct. But spin starts high later, right? The corrections to spin is the 2.5 pn that we are referring to is starting from the dominant non-spinning thing. So to go there requires quite a long time. We have only, what is it, 1 pn correction or maybe 1.5 for some cases. That's all we have in for spins. So forget about getting post-Newtonian theory accurate to such a high order. Any comments, Bala? Is it possible to just get the spins?
Last year it has gone to one more order, and in this APS meeting, Arizona was basically saying that in principle they don't see any difficulty going one more order.
But that's only for spins, but there will be other terms which will be neglected at that order, like
No, but so for example, let's say if you go to right now, I think you are at the level 3.5 pm also for the black hole kind of cases. If you go to 4, so the basic point is their feeling was that for the non-spinning case, what we are happy with at
Can I have this
5
fan?
PM,
Is it possible to get this fan?
4.5 pm for the spinning case.
I know it may,
So
yeah.
maybe over the next couple of years we can get to that particular orders, and things may be a little better.
Oh, but that still means the 2.5 pn of spin corrections, right?
See,
So spin corrections start at 1.5
The
pn.
problem was the black hole spinning case.
Yes.
We want to worry about.
Yes,
So there I thought that at least they had hope that they can deal with
they can, but what I feel is that you will not get to starting from 1.5 pm. If you want 3.5 pn corrections, if I do my arithmetic correctly, you have to do 5 pm in absolute order. Huh?
4.5 almost.
Okay. If you can get there, but at 4.5 pn you don't have the other correction, so you have only spin. So the problem is that you have an incomplete description, and it's not at all clear whether they will agree with each other. I think what we are talking about here, it became a little bit technical, but just to explain the way post-Newtonian theory proceeds, it starts off with some dominant term. You can call it Newtonian if you wish. So there may be a quantity called an, and then there is an expansion which in some quantities goes like, first term is absent actually, 1 plus v by c, v square by c square, etc. We are talking about computing the coefficients of these expansions at different orders for different effects. What we are arguing is that we will probably never know the full post-Newtonian corrections, including spins, up to the required order, where we can trust post-Newtonian theory. And I feel that numerical relativity simulations can have a fundamental contributions to make here in understanding in spiral part, not the merger part. And we see large differences in neutron star black hole in spirals, and that's where we need breakthrough, I believe. I know it's hard, but if you make one such simulation, I think the problem is nobody wants to take the risk. This is going to take 50 million CPU hours. I better spend it where, this is like astronomers, incidentally. Astronomers, they want to really look at where galaxies are. They never want to turn their telescopes to it, and there is nothing. Obviously, am I a fool? I want to look at things that I know where stuff is. I'm not going to point my telescope up in, perpendicular to the disk of the galaxy. That's what they're going to say. But many interesting things might be found in the plane perpendicular to the galaxy. Yeah.
So in this, you're talking about this issue that you will lose some of the black hole neutron star signals with current post-Newtonian models. Do you know the numbers in terms of how many signals you expect to actually lose? Because for a lot of the parameter space, you do actually capture them.
I agree. I think if you go to Harold was saying 0.9 in spin parameter chi is very small, and I agree with you. We don't know how many binaries form with that, but if you have spins greater than 0.9 for black holes and neutron stars reside in such systems, which I suspect might not happen, and actually Christian might tell us whether or not such things can happen, because if you let binary systems evolve, a lot of matter will will have to be deposited onto black holes to spin it up to 0.9, 0.95, and so on, so much so that it doesn't really form a neutron star black hole at all. So my feeling is that spins may not get so high. We are getting into discussion time, but I don't mind that because this might be one of the important points that I wanted to make. But if systems do agree, Mark, then it's possible that we will lose, in terms of overlap, it is 0.3, which means we lose 90%, 95% of the systems if we don't include spin effects. So, go on.
I would put a free question. Let's hope that the quantity overlap is for a line spin or for precessing spins?
It was precessing spins, I believe.
Is it for the same physical parameters or after some optimization?
Say it again. Say it.
Is it for the same physical parameters or after some optimization?
I think it was effectualness. Yeah, it is after maximizing, not faithfulness.
I think there's a particular orientation, so that again, it's a very small.
I don't know whether it's particular. I'm referring to Ian Harry's talk. You saw the, majority of the systems. You got that? Please do. No, I don't think they're posted. Oh, that's someone you okay. Did they post all? Yeah, they posted it a couple of days ago. It may not be available to everyone, but at least we in the LSC should have access to. And the results that I remember is that you lose pretty large. Okay, 2 other questions.
The other questions. If you don't believe in spin, black hole spins of 0.95, is this an argument not to look for them?
No, yeah. So what happens is if you start off with binary systems in which one of them goes supernova, forms a black hole, and you want to spin it up because natal spins are not going to be very large.
Okay, I understand that's the physical argument.
Yes.
Just because we don't believe the systems exist, we still don't need to look for them. Exactly the point. And precisely because people say, hey, they can't exist, I want to look for them. Because I have an instrument in which they will appear. Why not? Right? I can either prove them right by not seeing them. I don't know whether I prove them right, but I can at least prove them wrong by seeing them. Okay. And my final remark is it's actually not that bad as you make it out as far as numerical relativity is concerned. These systems happen to be the most interesting ones because they also have a lot of precision.
Exactly the point, yes. Absolutely.
They're fun to simulate.
Yeah. In fact, I was telling the authors of this paper to put a positive spin on spin. Because it's only when, the fact that you can't detect them with non-spinning effects means that there's a lot of information to be gained, and they agree, of course, but of course this paper may say more like, oh, we got to do long numerical relativity simulations for neutron star black holes. Anyway, so you can see that's a very hot topic, something that you could immediately jump onto and start doing some work, either modeling or studying other effects. Yeah.
So I just made a larger point. So we get PN, we use PN just to get the initial conditions for numerical simulation.
Mm-hmm.
How do we know how good they are? Because they are just
Very good question. The point is that we know Newton's theory works, right? We fly rockets and things like that, and they do work in the sense that we know that when V by C goes to 0, the initial conditions can be just derived from post-Newtonian theory. Guys agree?
We have binary pulsar tests.
Yeah, binary pulsar tests and so on. So I think it's a more or less good, but in the end everything has to come from observations. I agree, but I have no reason at the moment to disbelieve post-Newtonian theory when V by C goes to 0. So if you start off early enough, your initial conditions are going to be okay, but the problem is they are very long. 50 million CPU hours that I mentioned may be a joke. I think they will probably require far longer to get reasonable numbers and good, they have to test. They have to run many different ones, right? So it will probably take much longer if you want to do hundreds of cycles. Yeah, okay, good. So, yeah, and also, you can improve, for instance, numerical relativity methods themselves. You can make them faster. So there's a lot of scope here as far as I'm concerned. I don't have to do the work, so I can make the suggestion. That's easy. Neutron star is essentially non-spinning in this case, but the black hole is a lot spin, causes a lot of spin-orbit coupling. You saw Harold's simulation where the plane was going topsy-turvy, and that's the challenge. So the spin-orbit is the different one.
Just make one comment about this issue of whether or not you do very long, expensive simulations, or you try to just get a higher order post-Newtonian formula. I would guess that the amount of investment, financial and human, that you have to put into to get a few people to push the post-Newtonian series, whether it's actually much cheaper than heating up lots of supercomputers for the next 3 years.
I agree. And also, that's the compromise. That's the comparison you have to make. I mean, you can see sociological issues do come in. Yeah. Right. In fact, why is this so important? When signal to noise ratio is large, for example, in LISA, we'll begin to see departures from post-Newtonian theory from observation. So that's why this in red, numerical relativity simulations, but better analytical models. Okay, numerical relativity, I think you've heard a lot about this. It's important really to now get on to mergers of binary neutron stars and neutron star black holes, tidal ripping, ball mode instability, electromagnetic afterglows, off-axis emissions, etc., are all topics of current interest and very greatly pursued. The in-spiral merger of neutron star black holes in particular is very important, as I already stressed, cumulative effect of black hole spin and so on, and merger phase of binary black holes. Here, it's really not so important to get just the in-spiral phase right. It's really the merger and the ring down part has a lot of interest. The quasi-normal mode excitation and the spectrum of modes for different binary configurations. In the last talk, Harold alluded to some of these things, and you said high mass binaries really tell you only about the remnant black holes. In fact, some of the recent work that we have done shows that just by looking at the quasi-normal modes, you can actually tell what the progenitor binary was. So if you looked at all the higher order modes that might be existed, even without looking at the in-spiral part of the signal, right? You don't see the binary, you just see the black hole, the final black hole, you can tell what the binary was. So that's, I think, is a very exciting prospect, because it might so happen that some of these binaries, only the merger phase, the ring down phase might be visible because they're very massive. You don't see the in-spiral part. Can you still conclude something about the binary? The answer seems to be yes, because there are spectrum of modes, that are emitted, and by following those modes you might be able to tell what the progenitor binary was. Something that we started off, but there's quite a lot to go, and we need to build phenomenological models, effective on-body models, etc. for this merger phase. Supernovae, I think, Christian, you're going to talk quite a lot about it. Next week?
None of these students are actually next week.
Oh, really? I didn't realize that.
Last day of the school.
Oh, I didn't say anything about it. Sorry. Maybe you can ask Christian during the lunchtime about numerical simulation. So actually, oh, you're not going to be here. Oh.
The question
Yeah.
session this afternoon.
There is a discussion session.
I know, but I left out my colloquium slides, which I think, okay, anyway. All right. Small black holes falling into big black holes, etc. Analytical models of in-spiral merger. Let's actually not go on too much about that. I want to leave that because I thought it might be covered. I want to talk about what has been done with gravitational wave observations so far. That will be the main theme, but I want to tell you about what are the main things that motivate research in gravitational wave data analysis and searches. What are the challenges? Why do we need to develop special techniques? I have about half an hour, maybe less than that. Yeah. What I show you here in these two slides are what are called detector antenna pattern functions. I didn't write that down, so I'm going to put this in here. What are they? They tell you this. So this is what is called a Mollweed plot. On the x-axis, you have the right ascension or the hour angle, whichever you are familiar with, or just the azimuth angle, if you wish, right? Phi, azimuth angle phi, and that's declination or theta, okay, or the co-latitude. So this Mollweed plot, it's an equal area projection plot. So what it shows you is the beam of the detector network onto the sky. If you have more red places, sources coming from that direction are more brighter in our detectors compared to sources which come from these directions. Our network is less sensitive to sources in those directions. Okay? Now if you take a telescope, like an optical telescope, its antenna pattern will be a single dot on the sky as opposed to a pattern like this. Everything else will be that black, and there will be a single very bright red. That's it. That's the antenna pattern. Gravitational wave detectors are sensitive to most of the sky, especially if you bring in a network. If you bring in a network of detectors, like I have put 3 detectors, detector at Hanford and a detector at Livingston and a Virgo detector, 3 detectors. And the joint antenna pattern of these detectors is such that there is almost literally no spot in the sky from which a gravitational wave source can hide. But if you put 5 detectors, as in this slide, Hanford, Livingston, Virgo, India and Japan, the entire gravitational wave sky is visible to our network. Okay, it's an isotropic, the detector network is isotropically sensitive. Any direction we can see. Therefore, the challenge is the problem is the following: a network of network of gravitational wave detectors is always on to most of the sky. It's like taking a sphere and putting eyes all over it and keeping eyes open all the time. That's what it is, and therefore detecting sources from such a detector network is going to be extremely challenging, because signals can last either millisecond or last for years, or you could have multiple signals in band of different amplitudes, and sorting them all out is going to require a brain power at the middle in this detector network, which can discriminate all of them. And that's where you need to build intelligent algorithms to integrate. So we can integrate and build the signal to noise ratio by coherently tracking the signals in phase But the problem is it requires good algorithms, because we are seeing sources all over the sky, different amplitudes, different frequency bandwidths, and so on and so forth. So we require typically a lot of computational power, okay, just to do this discrimination between noise and signal. So what kind of sources can we see on the sky? You will see many plots of this kind, so let me take a couple of minutes to explain it. What's plotted on this is signal strength, or the noise power spectral sensitivity, not power, sorry, amplitude spectral density of not density, amplitude spectrum of different detectors. On this horizontal axis, you have frequency. Okay? We essentially listen to gravitational waves, because that's the audio band. You can see we start off somewhere around 10 hertz and go to about 10 kilohertz. That's where we can listen. So we can listen to gravitational waves if you wish, if they were strong enough. And let's first look at these red and green plots. This red plot is the strain sensitivity of initial LIGO detectors. Any source that is above that, we can see. If the source is below, if we can integrate for a long time, then we can see, otherwise we can't. Okay? So what's plotted then, in addition to initial LIGO, is this advanced LIGO detector. It's a frequency plot, frequency sensitivity plot. So you have to interpret this carefully. For instance, if you look at this binary system here, which goes like f to the minus 7 by 6, somebody asked, I think in the question and answer, why does it go like, it keep going even though the amplitude in the detector, sorry, the amplitude of the signal is increasing. We'll come to that later. But this is leaving a track like this. By integrating this as a function of frequency, we can build upon signal to noise ratio. So the area under these tracks below, above these lines is what gives you the signal to noise ratio of the detectors. It's actually the square root. You have to square this and then square that and then integrate, you get the signal to noise ratio. That's the signal to noise ratio square, and then you take the square root. Anyway, the point is that the area under these is proportional to signal to noise ratio. Advanced LIGO improves the sensitivity by a factor of 10, and that will then increase the search volume by a factor of 1000, because our detectors are sensitive to the amplitude, and amplitude goes like 1 by r. If you make your detectors 10 times more sensitive, you see 10 times farther, and therefore 1000 times more volume. So binary black holes leave a track like this. They go, keep inspiring. The merger phase is around here, and then they go merging. Okay? Binary neutron stars are actually more interesting than binary black holes, because the signal here is pretty boring, except in the case of maybe precessing binaries. Non-spinning ones are pretty boring, whereas binary neutron stars will have a lot of structure towards this final merger phase. Also plotted in that graph are things like the crab. If it has an eccentricity of 10 to the minus 6, is a little mountain which is less than a millimeter, and if it exists on the crab, and if I integrate, then it should lie here. So you might already start wondering whether advanced LIGO is likely to detect gravitational waves from crab pulsar. The big problem is we don't know what that eccentricity is. It might be, for all I know, 10 to the minus 9, an extremely round pulsar. And there is good evidence to believe that pulsars really don't have big eccentricity. So this might be actually way down there, okay, maybe way down here. So we might not be able to see it with advanced LIGO, but if it has eccentricity of 10 to the minus 6, that's where we will see.
Even ellipticity.
Sorry?
Ellipticity.
Ellipticity, yes. Ellipticity, yes. SCO-X1 is a low mass X-ray binary. There is a neutron star there, and if it's accreting mass from its neighboring companion, that's why it's an X-ray binary. And if its spin, which is halted for some reason or the other, is halted because, meaning, its spin is not changing as a function of time. If that is, actually the reasoning is a slightly more complicated one. We see many low mass X-ray binaries, the spins seem to be not greater than a certain value, something like 300 hertz or so. If that's the case, then there must be something that is stalling their spins, and if it is due to the emission of gravitational waves, namely gravitational radiation back reaction is preventing the star from being spun up due to the accretion of matter from its neighboring star, then we can calculate a certain gravitational wave amplitude looking at its spin frequency, and that's where it puts that amplitude. So advanced LIGO might be able to see if this is the reason for gravitational wave emission. Now it has many other sources. Let me now show you what will happen if you include a third generation gravitational wave detector called Einstein telescope. It will be able to see sources further, like binary neutron stars at z equal to 2, binary black holes all the way to z equal to 20 or so. I've shown the track here for z equal to 5, but even if you put it at z equal to 20, we should be able to see it. The other systems, I won't go into that, but I want to talk about the current status of gravitational wave observations from the most recent science runs of LIGO and Virgo. In fact, I didn't include anything about the current gravitational wave detectors, the status, mainly because I thought the students would be here on Tuesday. But anyway, so you have to assume that there are what are called LIGO and Virgo detectors. Did anybody talk about LIGO and Virgo at any point? No? Okay, sorry about that. I should have really talked about it. I didn't know. Yeah, okay. Now, this is again that strain sensitivity. This curve here, the outer curve here, that strain sensitivity as a function of frequency was the goal, the design goal for the LIGO project, and it was almost written by hand waving around 1991, 1992. And that was the goal. And LIGO was built, and over several years, it started operating in 2001. 2002 was the first science run, and that's the sensitivity. Orders of magnitude away from its final design goal, both in frequency as well as in strain spectrum. But over something like 4 years, systematically the sensitivity was improved, and the final design goal, almost the final design goal, was reached just in about 4 years. I would say probably 5 years, because there was also another run called S6 a little later, 3 years later, but 4 or 5 years is what it took to reach the design sensitivity.
So you mentioned that the original design goal was quite approximate. This was cooked up in 91. So was there any reason to expect that when they got to this design goal that they could have gone further with?
No reason at all, because in fact S6 sensitivity at higher frequencies is even better, without making too many differences, except laser. Laser was changed. Laser power was changed. So just to tell you, the three fundamental sources of noise here, at this end here is the seismic wall. The ground motion is translated into mirror motion at low frequencies. That's what limits this wall here. The second one is thermal fluctuations in a mirror substrates, and that's what is this power law. You can see that's one power law, the second power law, the third power law. Those are the three things that they wrote. They said we're going to use a suspension system, and that should have that kind of restriction. The thermal thing was actually more complicated. That's why you don't really reach there, but they got more or less what they wanted. And this is basic physics. This is photon shock noise, counting noise, square root of n noise. So that was very much under control. That's why they reached it. So those three fundamental sources of noise is what limits the gravitational wave detector. But if you go to slightly lower frequencies, gravity gradient noise is actually our limiting factor. I saw a question on that as well. So we'll come to that later in the discussion. Virgo also remarkably achieved its design goal with much better lower frequency sensitivities, although there is still some deficit. The reason for this better low frequency sensitivity is fantastic isolation systems, long towers that they use in their isolation systems. This is the latest LIGO 6 science run sensitivity, and if you go back, I mean, I didn't put the design curve, or rather whoever made this plot didn't put the design curve, but if you go back and compare at around 200 hertz, it's about 3 times 10 to the minus 23. So it's slightly better at this point. Okay, so the latest science runs have really exceeded. That's because they did some improvements. That was called enhanced LIGO, not quite a lot. So using those instruments, some gravitational wave searches have been carried out, and that's what I want to tell you about in the next 10 minutes.
Can you tell more about those peaks?
Good. We are in an environment where there are lots of oscillations, natural oscillations taking place. There are oscillators that are connected to the detector, right? There are frequency oscillators connected. There is simply the power line. The power line in the US is 60 hertz. Therefore, you will see a peak at 60 hertz. 60 hertz is that peak there. At 120 hertz, it must be that, and so on. So at every 60 hertz, there are harmonics, simply because of the power line. But also, these mirrors are suspended by suspension systems, and they have their natural frequency. In fact, one of the biggest goals is to make the suspension natural oscillation frequency such that all the power is concentrated on a single line. So there are some of those suspension lines. I can't tell you exactly where it is. I think this is one of them there. That's the suspension line, and and its harmonics as well. So these peaks really don't bother us so much because they are very, very narrow. Especially if you track them for a very long time, they become narrower and narrower. So we are not limited by that. It's really the envelope of those that bother us. And well, lot more to say about them, but I won't. Gravitational wave searches. There are different kinds of algorithms that are used. One is to coherently combine data from different detectors and integrate. But not just different detectors. Even if you look at data from a single detector, you can follow the signal either in phase or you can follow it in intensity. Electromagnetic detectors, most of them follow signals in intensity, not in phase. Radio astronomy is one difference, but one case in difference, but most of them really follow signals in intensity, whereas we can follow them in phase. We can use hierarchical methods, time frequency analysis, which are suboptimal, but when you don't know the shape of the signal, as for example in the case of supernovae or other unmodeled bursts of signals, it is better than nothing. It amounts to concentrating signals in time frequency space. However, the most useful technique so far, and the reason for computing these waveforms very accurately, is what is called match filtering. And here the challenge is to use templates and algorithms for placing templates optimally in arbitrary dimensions is a challenging problem, and one that is worth following for a PhD even today. And efficient parameter estimation method is also a challenging topic. A lot of effort has been put in the past about 5 to 10 years, but we are still not anywhere close, and it is actually sometimes shameful because we take more time to determine the parameters than numerical-relativity guys take to generate the waveforms. So that ought to change. We are not solving Einstein's equations. It cannot be that difficult, but at the moment we are not anywhere close to that. So searches for compact binaries in more than 2 dimensions is still a challenge. You might really wonder what these guys are doing for the past, including me of course, for the past 20, 25 years. You know, we can't do searches in more than 2 dimensions. Numerical-relativity guys can do simulations, sorry. I know. 3, see, you made progress in 20 years from 2 to 3. So including effects of spins, orbital dynamics, spin evolution, all this is very important. eccentric orbits might be there, which will bring in more information, and we have no search that addresses that problem. So we need to make progress. Importance of higher order post-Newtonian corrections, in gravitational wave searches and parameter estimation. Each one of these is a research topic, incidentally. I think one of the biggest challenges we have is we can't shut off our gravitational wave detectors. We really can't turn them off. Telescopes can simply put a lid in the front and measure what is called the dark current. And there is nothing you can cover your gravitational wave detector with such that it doesn't see any gravitational waves. So estimating the background is a very big challenge. We use methods to estimate it, but they are not probably the best ones, especially when gravitational waves are present in them. Okay? The way we estimate the backgrounds is assume that there are no gravitational waves in our detectors, and we estimate it. But if there are lots of gravitational waves, then we will never be able to detect them, except the very bright ones. It's like the confusion background. So that situation has got to improve. If you can make a breakthrough there, you get your job, not just your PhD. Okay, so that's a very, very important. Analyzing data sets that are hours or days long is a big challenge. We can currently analyze data sets that are about an hour long, meaning if the templates are about an hour long, we can analyze them. Very big breakthrough is currently being made in using something that Google developed for audio streaming data, but we still need to make quite a big progress when signals are days long. I'm talking about mainly compact binary systems. In fact, the problem with continuous waves can never be solved. Continuous waves which last for years, it's always going to be computationally limited. And algorithms for parameter estimation when multiple signals, nobody has even touched this particular issue. When there are 2 or 3 signals present in the same data, how do we extract the parameters? Nobody has even started looking at this problem, so you could get those things. I think I'm going to skip this and tell you some results because I'm really running very, very late. And unfortunately, I decided I'm going to do bullet by bullet because otherwise I thought I will go very rapidly, but it didn't help. So let's skip this and maybe, maybe this is a summary slide. There are 4 types of searches that currently take place in LIGO: compact binary coalescences, binary neutron stars. LOMA are called low mass searches. They are by no means really low mass. Binary black holes, they're called high mass searches typically. That shows you a numerical simulation of coalescence of black holes and emission of gravitational waves, final black hole formation in quasi-normal modes. Not a great movie. I think it's from a few years. The second type of search is what is called unmodeled bursts. If you have a supernova going in our galaxy, we should be able to see them, but we won't know what the supernova waveforms are going to be, so we will need algorithms that are robust.
Would I like to comment on this?
Yeah.
It's not that these waveforms are not models. It's that there is an intrinsic stochasticity in the wave emission that even if you have a perfect computer simulation code, you will not be able to predict the waveform because there's turbulence.
Unmodelable.
Yeah.
Yeah, not unmodeled, but unmodelable waveforms.
But
that's good. Yeah.
There's key information that you can predict, namely what is the time frequency evolution of these things.
That you can do. Yes, exactly. Yeah.
But you cannot predict the actual curve.
The phase. They can't be followed in phase, but they can be followed in time frequency. And so the idea is to use algorithms that are suitable to what people like Christian Art can tell us. Okay? That's what these guys went after. So they can use whatever information you can give and tune the algorithm, and they are called burst algorithms. And they can search for different things. But the one that is really computationally most limited are continuous waves from rapidly rotating neutron stars. Radiation from known pulsars, it could be, or it could be from all sky, you do a blind search. And pulsars in binary systems, that's one of the very challenging ones, like the SCOX one. where we know it might be emitting gravitational waves that are detectable in advanced LIGO, but we are severely computationally limited, and we also don't know enough about that system. We don't know the orbital parameters of the system. So this particular one, to me, is a very good research problem currently and might lead to detection of gravitational waves. Stochastic radiation, unfortunately, is not something that's going to be very interesting, my personal point of view. Don't think that that's the universal opinion. Here, I don't think we will see radiation from known pulsars. Again, personal point of view. A lot of research has gone in there, very sophisticated algorithms, but unfortunately we won't see them. There is a good chance that one of these two, even this all sky, all blind searches, maybe, maybe not, but this one, last one here, pulsars in binary systems, may be our best at, but not stochastic radiation, although there are some very good algorithms that are being developed.
These are unknown pulsars in binary systems.
Yes. Oh, no.
There's known pulsars.
Known pulsars like SCO-X1 might be an interesting system.
So they are brighter than isolated pulsars?
They are more likely because they are accreting matter and therefore likely to have some quadrupole anisotropy that will lead to detectors. Okay, a very brief thing about in-spiral search pipeline. Data comes from different detectors. You create template banks for each of those detectors because they may have different power spectral density. You match filter each of those data sets and you combine them and look for coincidences. This is what is called a coincidence search because you're not bringing the data together to begin with and then analyzing, which will be more sensitive and more robust, but rather you are doing this poor man's choice of doing the analysis of different detectors first and then performing coincidences, and only after you perform coincidences, you again create a sub-template bank, what is called a sub-template bank around the parameter space where you found the signals, and then you actually follow them up by using chi-square, what are called chi-square tests. These are simply signal consistency checks. You're looking for black hole binary waveform, and you want to first check whether the signal in your data is in phase what you expect. So if you don't compute your numerical relativity waveform, you will actually be rejecting true signals. That's why we need these guys to do their work very, very hard and make sure that they are giving us right waveforms. Because we apply those consistency checks and reject waveforms which don't follow into that category. Therefore, we need those tests to be robust, and good waveforms are needed there. And then we apply lots of data quality checks and so on, and then use what are called time shifts to perform estimation of the background, and finally we compute either upper limits or the rates. Binary neutron searches use, as I mentioned already, match filtering. Merger phase of the signal here is very unimportant. We don't need to bother. Spins are not important either. That can be neglected. And we search in two-dimensional space of the two component masses. The component masses are varied from 1 to 24 solar masses, and total mass from 2 to 25 solar masses. So it's a two-dimensional template bank. And the distance reached during S6 for binary neutron stars and neutron star black holes in that parameter space is plotted here as a function of total mass in spiral distance. At lower end of the masses, it's only tens of megaparsec. That's all our distance reach is. Whereas at high end of the mass range, we can see systems up to hundreds of megaparsec. So we go and apply that in-spiral pipeline that you saw, data analysis pipeline. We look for signals. We did that, but we found nothing but one signal. Unfortunately, probably nobody told you that we already detected a gravitational wave event called the big dog. It was called the big dog because it occurred in the constellation Canis Majoris. Instead of being sophisticated and calling it Canis Majoris event, we used the English language and called it the big dog event. And here is the plot to show you what we detected. What is plotted on this is the cumulative rate of events that we see in our detector as a function of threshold that we see. Rate of which events? Not just gravitational wave events, any event that comes through our detector. all we can do is to apply a threshold which is something like 8, and then as you keep increasing the signal to noise ratio, the number of events keeps dropping. How do we know whether it's a gravitational event or something else? What we do is, in that coincidence such that you saw, you get an event, let's say today at 12 noon, and one at 12:05 and so on, they're time stamped. You get it from another detector. What you do is you artificially time shift from the second detector and compare the events from the two and look for coincidences. If the time shift that you have is larger than the light travel time between the two detectors, then this can only be an artificial coincidence. It cannot be a true gravitational wave event. Okay? So that means that this is a background event, provided the gravitational wave events that are coming in our detector are very rare, they're not very frequent. Okay? So in this way, by time shifting and cross correlating, we can estimate a background in a detector where we don't expect to see many gravitational waves. Our astronomer colleagues tell us that you won't see many gravitational wave events, and that's why we do that. And those are the black dots that you see, black dots here. There's one estimation there, the another estimation, I'll come to that in a minute. The blue crosses are when you don't do any time shifts. The blue triangles, I'm sorry. Okay? The blue triangles are that. Forget about this shaded region. They're slightly more complicated. Let's not worry about that. Forget, just look at these dots and these triangles. The triangles are also falling. So probably most of these events are really the background events, but seen in zero lag data. Whereas this is really truly background. They can't be gravitational wave events. What we saw was, lo and behold, we saw an event at a signal to noise ratio quite large and so rare in our time shifted data. If you follow this curve here, computing the noise background, and those are the two results, and we did detect an event. But we were about to publish, we wrote the paper, we were about to send it to PRL, but then we have a scheme by which we secretly, or some people in the collaboration secretly, but with the knowledge that they are secretly injecting the data, they do that once in a while. Okay? So before we send any of our paper to publisher, we open the envelope, the secret envelope, to see if there is anything inside, and lo and behold, there was this event. Okay? So we had to stop, and we had to curb all our excitement and cancel our tickets to Stockholm and whatnot. That's what happened. Anyway, this was a fantastic experience because it showed us that we can actually detect events that are present in our data, even if it is put secretly. No matter, it doesn't matter. It taught us a lot of lessons, both sociological and scientific. But this event is not really very loud. If you take the rate at which we assume, in injecting that event, it was only 30% closer than our horizon distance. Okay? So it's not particularly loud event. So it demonstrates that we can detect signals with very high confidence. I think I'm going to stop there. I have at least another 20 slides, so it's not going to be over. I think it's best if I just very quickly show you that we have not detected anything. We are still setting upper limits, and they are becoming interesting. So what we do if we don't detect anything is simply to say an upper limit on the rate of binary neutron star mergers. Those are the two boring slides. This is the interesting slides, which shows the rate estimates in units of megaparsec cube per year, and these gray areas are our upper limits. Okay? How does that compare with astrophysical predictions? Those are in the blue. As detector sensitivity keeps improving, we keep improving this rate. How much more can we improve? Well, we can improve the rate by 3 orders of magnitude with advanced LIGO. Now you can see why there is so much excitement with advanced LIGO. You improve these rate limits by 3 orders of magnitude. Forget about these two, because these are really science fiction at the moment. We don't know if they exist. We are really after this. Advanced LIGO, or LIGO, was really built to detect binary neutron stars because we know they exist. And the nominal rate is there, 10 to the minus 6. And what do you see here? 10 to the minus 4. How many events do we expect? About a few tens per year. Because when this improves by 3 orders of magnitude, that's our rate upper limit now, the bottom line there. And that's the reason why there is excitement. Let me stop there. I think there's no point in going beyond.
Thanks a lot, Satya, for this excellent introduction to the topic as well as a survey of the current research. Now, I guess all of us know what we should write in our next paper. So we have time for a couple of questions that we can follow this up in the...
You can always approach me and ask me later on.
in the discussion session.
Yeah. Yeah, any quick questions? Yes.
I don't know if it's going to be quick, but the point where you said from quasi-normal modes you could detect the initial conditions from the binary, is that considered a violation of like
Exactly, yes. I mean, that's what you would think initially. Because quasi-normal modes, all mode frequencies depend on only the mass and spin of the black hole. How can you tell what the progenitor was? But in addition to the mass and spin, we can also actually measure the various modes, amplitudes. Those mode amplitudes contain information about what perturbed the black hole. In other words, what we are telling is you can know about your initial conditions if you can measure the different amplitudes, because the different mode amplitudes depend on what the perturbation was. Our research is really not formulated in such a sophisticated manner. I'm saying it. What we did was to look at the behavior of different quasi-normal modes and found that they critically depend on what the initial conditions are. But we have done a very limited study. The full parameter space is something like 7-dimensional. We have done study in only 3 dimensions. Oh, 2 dimensions. Would you say? 2? Well, spin and mass ratio. Right? That's it. So 2 dimensions. So it's not the final word, but I think speaking from a very conceptual point of view, it's true that you should be able to tell what the perturber is if you know what all the modes are, and that's the point. There may be some degeneracies, but that's not a big deal. There will be degeneracies even in the inspiral mode. So that's the whole. Okay?
Okay.
Hello.
Can you go back to the big dots now?
Yeah.
The one with the pulsar outlines? What are the black solid circuits?
The black ones, yeah, okay. I left it out only because it's a bit too, well, it's an important one, and one that was debated like mad within the collaboration. These ones here, the gray including the black ones here, are computed, those are our backgrounds computed without including that big dog event in the background estimation. You can take that event out. You can claim that this is my philosophy and very heavily opposed by some of the very respected statistical people in the collaboration. My point is that I'm a Bayesian. I'm going to claim that that is a gravitational wave event. What should I do? I should not include it in the background estimation. So I won't include it, and then you get this background. And if you compute what is the probability that I will see this due to purely noise fluctuation, that will be something like 1 per million years. But our colleagues from LIGO and other statisticians would argue, look, you don't know if it's a gravitational wave event. First, you should compute your false alarm rate. It may be a very rare background event. So include it in your calculation of the background, and then it drops down by roughly 2 orders of magnitude, it elevates, and I get still once in 7,000 years that this event is caused by a pure chance in instrumental noise. So those are the 2 different estimates. Yeah.
So I guess in here you must have had lots of triggers that were much higher threshold but were excluded by...
Oh, yes, of course. Yes.
So they are all excluded. There were nothing...
Yes. Yeah. In fact, I started preparing this slide showing how we make our data Gaussian, how crappy it is to begin with, and what are the 4 steps that we take in order to make it look almost like Gaussian. I didn't. So if you did not have these beautiful techniques, Beto techniques, including the chi-square, which rely on accurately knowing what the waveform is, we would have had many, many more signals. We wouldn't have been able to do that detection. That's correct.
break for lunch at the moment.
Absolutely, yeah.
Come back for discussion at 2:15. You will have a group photo.